Hello guys and girls, welcome to a new clip in the C# for Beginners playlist, where I will try to explain in simple terms what data structures are, which are the most important ones and how to use them. When it comes to data structures, there are a lot of specialized ones, but today I'm going to focus only on the most popular ones that you use daily or that you should at least know about. Array is such a data structure, and I talked about arrays on this channel before, so I'm not going to focus on them much, but basically instead of a single variable you have a collection of multiple values of the same time packed together in the same variable. The problem with arrays comes from the fact that they are inflexible and inefficient if you don't know their size beforehand or if you need to resize them later on. Because the resizing is actually done by declaring a new array, copying the data from the old one and marking the old one for deletion. So for example, if you have an array of 1 million cells and you want to make it bigger by just one cell, you need to allocate, copy and mark for deletion all those million cells, which is pretty inefficient. And because of that, we have the next collection type, which is the generic list, which sorts of acts like an array, but is much more flexible. So even though internally it still uses an array to hold the data, the initial logistics of the initial assignment and the resizing when needed is much better handled and efficient than if you'd use a manual array. So let's see how we declare one. And of course, this can be shortened to this. And we can even use the common collection initialization syntax. And we can use it like this. So I declare a generic list of t, where t is string. If you don't know what I'm talking about, go watch the video about generic types. And then I use the add method to add two elements, and then I use a zero base index to access the first element in the list, just like we do in the case of arrays. And just like in the case of arrays, I'm also using the index to alter the value of some element, the second one in this case. So again, it sort of acts like an array, but you don't have to deal with the nonsense of already knowing the size beforehand and the pains of resizing and all that. All that is abstracted away and handled internally, and because of that, probably the list is the most popular data structure. You will use it the most. Other notable methods of the list are add range, when you want to add multiple elements at the same time, remove, sort, clear, reverse, find, contains, and others. One thing worth noting is the fact that while for arrays we have a length property that gives us the number of elements in that array, and we can use it to iterate it with a for loop or something, we have the same thing for lists, but this time is called count. So again, for lists is count, for arrays is length. Just remember the distinction. The next most popular data structure, but serving a different purpose, is the dictionary. And you can think of it just like a real-life dictionary, where you have words and they have definitions. And these words are unique. You will not find the same term defined twice. And the same is true for the dictionary data structure too, with the only difference of these terms being called keys and their translations being called values. So each element in a dictionary is actually a pair of a key and a value. And because of that, the dictionary class is double generic like this. So I declare a new instance of the dictionary of string int class, the string being the key and the int being the value. So in this case, I add two elements using the same add method. The first element being a key called Jane, the string Jane, with the value 20, and the second one, the key is John, and the value is 19. In real life, when you try to access a value from a dictionary, so in other words to get the translation of a word, you don't search by a numerical index position, you search by the word itself. So in the same sense, in a dictionary we search by a key, not by a numerical index like in the case of arrays. So something like this. Now beware that if you try to add the same key twice, or if you try to access a key that doesn't exist, you will get an exception. So because of that, we have a method that helps us protect against that, which is contains key, which does exactly that. It checks if a dictionary contains a key or not. The problem with this is the fact that we search the dictionary once to see if it contains this key, and a second time to actually get the value of that key, which obviously it's inefficient. So we have another method called try_get_value, like this, where try_get_value returns a boolean. So it's saying if the value exists and could be taken or not. And that's why it's inside an if. But if it's returning a boolean, we also need the value itself. Okay, you can or can't take it, but where is the value? So that's why we haven't talked about out parameters, but basically it's a way to not providing a value to the method in this parameter, but actually take a value from it. So it's an out parameter, it's giving us a value, not asking for one. So if the value exists and it can be taken, the method returns true. That's why it's placed in an if, but it also gives us that value inside this int age, and we can use it as if we declared an int variable further on. So now we can print the value if it exists. Another notable method is contains value, which obviously, just like contains key, tells us if a dictionary contains a value or not. And like list, we have other methods like clear, remove, and so on. The trickiest thing with dictionaries is the fact that since we can't access them with a numerical index, we can't iterate them like we would normally with a list or something like that. But for that we have two very important properties which are keys and values, which the keys property gives us a collection of the keys of that dictionary, and the values obviously a collection of the values it contains. And we can use those keys, the list of those keys, to iterate them something like this. And in this case, we iterate the keys collection, and for each of these key, we use it to access the dictionary. Another popular question is, how do I store multiple values for the same key? Now, you can't, not directly, but since the dictionary has both the keys and the values generic, so they can be anything, we could, for example, use, I don't know, the keys to be numeric, or the values could be an entire list of something. We could have an element where we have a key, which is a string or a number, and the value for it is an entire list. Or we could have an instance of a class to be the value, like for example, we could have a string name as the key and an instance of student class as the value, where the student class has multiple properties inside it, and so on. Lists, arrays, and dictionaries are the most important data structures, and you really need to know them like the back of your hand. But there are a few other data structures that, while you don't necessarily need to know all the details of them, you should at least know they are there and what they do, when you should use them. Like for example, the next data structure that I'm going to discuss is the stack, and we already semi-talked about it. I alluded at least about the stack data structure when we discussed about the stack versus heap memory. Now, you can think of a stack like a pile of clothes. You add new clothes at the top of the pile and you take from the top of the pile. And this behavior is called in programming LIFO. Last in, first out is the acronym for it. So we could theoretically declare a stack like this. You can see it's still a generic data structure, so we can use a stack of anything we want, and we add new elements to it using the push method instead of add. And we can take elements from it using the pop method like this. But beware that pop method also removes the element. So again, just like the pile of clothes example, you take the element. To get the value, you also remove it from the pile. Now, sometimes obviously you want to see the value but not necessarily take it. And for that we have the pick method, which allows us to pick, to just see what the value of the top element is without removing it. The next data structure, the queue, is exactly the same thing as a stack, with one major difference. The stack is a LIFO behavior, like I explained. The queue is a FIFO behavior, first in, first out. So we declare it like this. So it's just as generic as a stack. Now, this FIFO behavior, you can think of it like sitting in line to pay for a product. The first person that was in line will also be the first person to pay. And new people that are added to the line are added at the back. So in both the stack and the queue case, we take items from the top, respectively from the front. But for the stack, we add elements at the top. For the queue, we add elements at the back. This is the only difference. Of course, we also have different names for the methods. In the case of stack, we add elements with the push. In the case of queue, we use the enqueue method. To take elements, we use pop for stack, dequeue for queue. The pick method remains the same for both of them, so we can pick at the next value using the pick method in both cases. And both of them contain other useful methods like contains, clear, and so on. One example where you could use a stack or a queue or etc. is an undo-redo system, where instead of keeping a list of the actions that you performed and the order they were performed in and the position where you are with the undoing and redoing, instead of doing all that, you can use a stack or a queue to do exactly that. Another niche data structure, but very useful at times, is the HashSet. And you can think of it more or less like a list, but with the main characteristic of not accepting duplicates. So if I have something like this, you will see that even though I added London twice, the element is only present once in the collection. So it is very useful when you have a large amount of data and you want to deduplicate it without any pain. The next data structure that you should know about is the linked list, which is a collection of nodes that point to each other. So you can think of it like the node A pointing to node B, pointing to node C, and so on. So they reference each other, but in a certain specific order. And there are methods like add last, add first, add after, add before, and so on. They even have a method called find. But know that linked lists are not that used in practice. They are for very, very specific cases, so you should not necessarily stress yourself about it. Just know that they exist and the gist of it. Other data structures that you may hear about in .NET are sorted dictionary and sorted set, which are exactly like a dictionary or a hash set, but they also keep their elements sorted in case you need that kind of behavior. You may also hear about an array list, but avoid that. It's just there for backwards compatibility for historical reasons. It's the non-generic version of a list, so just use a list instead. You should also know that a class which contains properties can also be thought of like a data structure, a custom data structure, right? If you have a class called student and it has the property name and the property age and so on, it holds data. It's a data structure. It's a custom data structure. You can define one with whatever properties you want. So also know that. I hope you took something useful from this clip, because usually data structures are one of the most complicated topics in the curriculum of computer science in college. But it doesn't have to be like that. Just understand how it works and when should you use it, and you should be fine. So again, if this helped you, don't forget to like and subscribe. It really helps this channel to grow. In the next lesson, we will start talking about the first of the 4 pillars of object-oriented programming, encapsulation, and I promise it will be fun. But until next time, thanks for watching, and I'll see you in the next stack frame.